hear me? Yeah, good, thanks. Okay, so this is a workshop. We're down here in the cattle trading room, so feel free to interrupt me with questions. My goal today is to explain our open source project, Ezekiel, tell you how to build an application with it. And first, of course, we have to spend a few minutes on why it's interesting. I think if you're here, you probably have some idea of that, but okay. So people like AI, it's the hottest thing. But in reality, of course, it's been a big part of what powers large and small organizations for a long time. It's centralized. It requires trusting the person running the AI. But of course, it's familiar Python workflow. There's lots of models we can work with. And then we have smart contracts. Smart contracts are decentralized. They're trustless. And they have this wonderful composability property that we can only get through sort of an API. So it's a much stronger form of composability than we could get in off-chain ML. But they're not that scalable. We have to run the same program many times. We have to pay a lot of gas. And it's too slow and expensive for AI programs. And what does ZK bring to the equation? Well, it preserves decentralization, trustlessness, and composability, but it adds in a scalability, right? So now one person can compute a proof on one machine, and everyone can believe that they did the correct thing. They did what they said they did. And that lets us have another level of composability, but we have some downsides. We have to learn a weird language. We have to think about programming circuits in some kind of unfamiliar model, and the math and the security is difficult. So the big picture about what a zero-knowledge proof is it's a lot like a digital signature. It's just that a digital signature has public inputs. It has a private key. It has a signature function that we compute as a function of those two things, and we get a result, and we get a signature. And then we verify it on-chain, or more precisely, at the protocol level, the chain decides have you signed the thing or not. Okay? A zero-knowledge proof lets you replace this signature function with any function you like, and we're here today because we think it's interesting to replace it with a machine learning model. Then we get something that combines all these properties. It's decentralized, it's trustless, composable, it's scalable because one person can make a proof that everyone can believe. But we can also get our familiar Python workflow, libraries of existing models, and hopefully we'll be able to power some kind of on-chain organizations, right? So if off-chain organizations need to deploy ML to run, and we're building everything new institutions in Web3, we're going to need to run some of these programs too. And our goal is to make that super easy. Basically, you describe what you want to do, you build the model in Python the way you always have, and then we help you to build and deploy it into a pipeline. So what does a pipeline look like? Basically, it has four parts. There's some kind of truth from the world. You download a signed piece of data from a news organization. You download a piece of data from the chain that's attested to, and then you check a signature. That's ingestion. Then you run the model, which proves that you've computed this function correctly. Given these inputs, if you believe them, you get an output. Then we verify it. Because we're here at Denver, we only care about verifying on-chain, but of course, there are many other possible ways to do it. And then we have to do something, like fire off a hook, enter into the index, or let a smart contract do what we ask the smart contract to do. And again, our goal is to make that kind of a simple process. Build your model in Python, define your pipeline, and deploy it. And just to talk high level for one more minute, why ZKML? I like to think about it as we're giving the blockchain eyes and sensory organs with which to perceive the physical world. We're giving Ethereum eyes. Let it interpret ambiguous events. Long term, the reason I got excited about this is that I think this is the way to make it possible for humans to own digital assets, in the sense that the chain will learn an ensemble of models that knows who I am. If I lose my private key, it's no big deal, right? It doesn't all depend on some single point of failure. Just like I own my assets and my identity in the society in which I exist by a whole host of different relationships, and if my house burns down, I can still walk into the bank and prove I am who I say I am. I think we need to get to that future for broad adoption. I think this is the way to do it. Of course, we're a long way from that. However, I think that the longer I've worked on this, and lots of other people do great research and work, I think that future is getting closer extremely fast. I also say that it's kind of a way to make smart contracts exercise judgment. Put the smart back in smart contracts, right? We can have a smart contract now that is as smart as a human lawyer, or maybe smarter, that can make decisions about, did someone fulfill the bargain that we made with them? Did they, if they were contributing to a DAO, did they, build the web page we asked them to? Did they run the errand, whatever? Those kind of things, so that we can someday all work for, AI on chain, which maybe not, but okay. So I want to talk quickly about some application examples, and then I will go to the repo and talk to you about how to use it to build something. So one application that a lot of people are excited about is vaults. So there are protocols like Arrakis that force a choice. This is just a quote from their website. Apologies to them if anyone's here. So you have basically two options. You have trustless vaults with predefined on-chain strategies. They're in a smart contract. They're trustless, they're automatic, but they're simple and they're not private, right? They're public. Or you can have managed vaults that have sophisticated strategies. Depends on somebody downloading the data, running on their laptop or on a server. You have to trust that person that they won't suddenly buy some token they just created. So they require trust. And of course, ZK fixes this because it lets us have automatic, trustless off-chain strategies. This is a DeFi section, so this is important to emphasize. In other words, I can define a strategy, I can commit to it. It can stay private if I have great alpha. It can run on the chain against this vault for any period of time, 2 months. I see the performance. People can invest in that strategy and know that they're getting exactly the same model that was previously running. So it's like forward test, which is really cool. And you think about it in the context of something like an AMM, I came from originally a traditional finance background, and I thought AMMs can't possibly work. They leak all, you're trading a public strategy, it's just going to leak everything, right? And to some extent they have, and they make up for that with fees, right? So, but what ZK lets you do is have, at least in theory, one of these things that where some of its strategy is private. And so it doesn't leak as much information, it's not as easy to trade against, and therefore it can charge lower fees, right? So it can make everyone else a little bit better off. It's like a reduction in the deadweight loss. Here's an example of one of these that is being built by some folks here that lets you define a bunch of parameters in terms of what you want a vault to do, and then it recenters it periodically. In this case, like every 12 days, it would run the machine learning algorithm through a zero-knowledge proof. There could be triggers that additionally do it, and you get some kind of definition. And in this case, it's a fairly simple concentrated liquidity management manager whose parameters are being managed by a machine learning model. But you can imagine that in the long run, this is going to be a much more sophisticated object. And what these folks want to do is to build a kind of like a no-code, low-code tool that lets you create DeFi strategies. And the way that we enable the flexibility of those strategies is by being able to compile them on the fly into a proof. And that's what the role that Ezekiel plays. Here's another project that's being built this week called NPC Wars. It's kind of a decentralized Kaggle. People can compete using their AI models against each other in on-chain competitions. They upload their resulting great Onyx file. Ezekiel generates the verifier and the proof, and then the winner, the person who had the best model, wins the prize. Their design is so much better than mine. I just can't even. Anyway, so this is the design. It's like you have your model is an NPC. These are the 4 authors of this, and you can create your model and then fight and watch the leaderboard. And another one that's really cool is the Scavenger Hunt application, which is, where is it? Oh, it's on the, sorry. Here's the demo. So it's called Hunter Z Hunter. It's a scavenger hunt for images. And this is kind of like a pilot for identity, right? So someday this will be your face instead of, maybe someday might actually be like 2 months from now, but someday it'll be a face. And the basic idea is you create a hunt, you give a hint like I'm green and full of chocolate, you give the hunt an end time, and you choose a photo that's your target photo. This enrolls the image using a zero-knowledge proof, with Ezekiel running in the background. Then the hunt is created, and then you can, as a player, see, oh, here are the prizes for the different images. If I can find the photo that will unlock this, or that will make this neural hash, then I get the prize. So in this case, if you submit the wrong photo, it will tell you there's no match. If you submit the right photo, then it will show you that there is a match, and create the proof only then, lazily. And then when the proof gets submitted to the chain, that unlocks your prize and sends it to your wallet. And so that's a game that should be playable before the end of the hackathon for anyone who wants to try that out. Great, so now let me switch gears and just talk a little bit about the repo itself. So I'm going to talk you through just a little bit of the README. My goal here, again, is to make it so I don't want to build any applications. That's not my thing. I don't know how to growth hack or do anything like that. My goal is to let you build an application with the minimum fuss. This is our repo. It's supposed to be easy zero-knowledge learning. It's getting easier. And what it does is it lets you define a computational graph for usually a neural network, but it could be something else. You take that final graph, you export it as an ONNX file, which is basically just if you dump the abstract syntax tree of the forward pass of a Python model, that's what it is. It's not very complicated. And then you point Ezekiel to the ONNX and the JSON files, and that generates a circuit. You can prove that I ran this public network on a private data to produce this output, like in the Hunt example. I ran a private neural network on some public data and it proved this output, like in the Percept ZK Vault demo. Or I correctly ran this publicly available neural network on some data, and it produced some output in like a public oracle. I want to prove that I want to make a market for predictions, and I want to prove that I downloaded a story from a reputable news source, if you can find one, and that someone won an election or a hurricane hit, something like that. We use Halo 2 in the back end. We love contributors. Please contribute. You have to use nightly build Rust, so sorry about that, but otherwise it's not too bad. You can install it with cargo install. There are documents, so there are tons of tests. We spend lots of scary money on tests so that we run every single one of the proof pipelines on tons of examples to make sure that nothing breaks for you. There's full documentation. Every function, every struct is documented if you want to read about the details of the internals. And let me just walk you through the command line, because I think that gives an intuition for what we can do, right, what we're doing. So once you have a command line tool, Ezekiel, the first line here is gen SRS. So is this okay. All right. So the first line is, maybe if I increase the size a little, is that better? Yeah? Okay. So the first line is, this is using KZG commitments because we want to compile and verify on Ethereum. So we can either use a public ceremony, or you can generate your own SRS. That is for testing only and is not secure. That means the person who generated that can generate false proofs. But it's just as easy if you download one of the Powers of Tau ceremonies, you can use that. And then you ask it to prove. It has some parameters, which I'll explain in a second. And it takes an input file, that's like the image, the picture of the chocolate bar or whatever, which is as JSON file. It takes a model, which again is an ONNX file that you export from Python. Let me show you how one of these ONNX files gets created. Oh, right, there's no internet in here. Okay, maybe not. Basically, there's a very short Python program you write. You say import torch, import Ezekiel. You define your model, PyTorch, subclass of that, and then after the forward pass, same as completely standard Python, and at the end you say export. Export this model with this input, and then that will create the ONNX file for you. There's examples in the repo. Right. So then you run the proof, and with this model file, and then you tell it where you want to put the proof and the verifying key, and load the parameters, and then that will compile the model to a circuit, generate the proof that this model, when you took these inputs, private by default, this is a proof that the inference was run correctly. You can also verify, again, using the network file, and this time not the input, but the proof. So now the original input of the proof is possibly secret. I don't have to reveal what picture of a chocolate bar I created, or I don't have to reveal my strategy in a DeFi vault. And then it produces, we'll verify it directly. There's also a table command that will just print out for you what our strategy is for turning the model into a proof. So it'll sort of show you how it gets compiled and what decision we've made at every stage of the creation. We can also verify with an EVM. I should say what these parameters are. So these two parameters, bits and k. So one of the funny things is that is the way nonlinearities work, right? So nonlinearities, what is a deep learning model? It's just a bunch of matrix multiplication, ax plus b, and then you hit it with a nonlinearity, and then you do it again, right? And there's some other details, but mostly that's all it is. Yeah. Yeah, so the question was, I can't repeat the question. But let me rephrase so what we're doing is we're using an Onyx file, a Python model, as a spec for a zero-knowledge proof, as a description, as a high-level language, and then we're turning that spec, we're compiling that spec into a circuit and running the circuit. I don't know if that helps. Okay, so bits at a technical level, we're doing ax plus b, and then we're hitting it with the nonlinearity, like ReLU, which is like, if it's less than 0, give you back 0. If it's more than 0, give you back the thing, or sigmoid function, or whatever, nonlinearity. And when you have to quantize, and when you implement a nonlinearity, a really nice way to do it is with a lookup table, which is a zero-knowledge proof thing. A lookup table basically does the following insane thing. I'm going to write down every possible input value of the function and the matching output value, and I'm going to prove that in my trace, everything that came out is somewhere in that table. So that seems incredibly inefficient and insane, and yet it's the best we really can do so far. Those arguments have gotten better and better. The nice part is that cost is constant. So even if my function is super complex, if I say, give me ReLU of sigmoid of tan, divide by 7, blah, 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 that all gets compressed into one table. So that cost is kind of constant, and that's just a hint of how weird the cost model is when you think about zero-knowledge proof as kind of like a computer, right? It's a very strange cost model, and we're also figuring out kind of what works well. Anyway, that's what bits is. Bits is how big is that table. So this means I'm writing down 2 to the 16 input and output values. That's adjustable. The quantization scale is adjustable. Use a fixed point arithmetic, and you can choose 2-bit representation or 16-bit representation, whatever you think works for your example. Yeah. And let me get to verification with the EVM. Ezekiel gives you 2 options for verifying with the EVM. You can either generate a direct EVM verifier, which is a single smart contract that runs the whole verification loop. Right now, this can only handle small things because there's some optimizations that need to be done. But it works, and that creates a Solidity file that has a verify function that's exposed. You can deploy it, and you can just call that verify function from your other Solidity contracts. And the other strategy you can use is using proof aggregation. This means you're doing a 2-stage proof. Stage 1 is this one, a single proof, where we feed it into, we create a single proof, like a device or something. It's fairly easy to create. It uses a different kind of transcript for the cryptographers. We're using a hash-friendly function, ZK-friendly hash function in order to construct our cryptographic sponge so that it's easy to check inside of the next proof. Then you generate an aggregate proof which kind of compresses that first proof into something that's much easier to check on the EVM. That aggregation proof can be very time-consuming and use a lot of RAM. And then you generate the verifying code, and give it a deployment path parameter, and that will let you, deploy that and check things against it. And these circuits are the ones that the examples that I gave earlier. The people that are building here at the hackathon are using these verifiers to deploy it on-chain. And then we can test that verification works by using Foundry Anvil in the background to run the EVM for us. And we also have some deploy commands. If you're feeling reckless and you want to put your mnemonic in a text file, hopefully just for testing, you can do that. And we're just trying to make your life as easy as possible to play with this stuff because it's really fun. And then you can even use the command line to send the proof. Some of the folks that are building on it this week have also built an RPC client that you can talk to, and so you don't like to use the command line, so you can talk to it directly from JavaScript, and we'll release that probably in the next week. And then as I mentioned, you can use a pre-generated structured reference string. And let me just talk through the commands for a second, and then maybe I'll leave 5 minutes for questions. So table is the command, again, that does the layout. So let me say a little bit what the strategy is. So when we started doing this, we were handwriting circuits, right? So you see it, you print out your Onyx file, or you write down your Python thing, and you say, okay, I need to do these matrix multiplications. By hand, I can put all that into circuits in Zerocom or in Halo 2, right? Those things are going to be fast because I can customize it, and if I have an overflow error, I can adjust things until I can fix that overflow error. And so what we're trying to do is to let you define the circuit by just writing some Python. And so we tried to put all of our modest intelligence into the compiler, so that the compiler will decide for you, come up with a strategy. How do we think we should quantize this? By quantize, I just mean you have floating point numbers. We can't work with floating point numbers. All we have is field elements. So what we do is multiply by something, like 128 or 256, round it, and then think of the integer as the numerator and the 128 as the denominator. And then you have to kind of keep track of what all the denominators are as you pass through. And this leads to all kinds of interesting numerical problems, which are kind of fun math. Anyway, so we have a strategy for that. Table kind of tells you what's our strategy, what do we think could go wrong in terms of values and overflows, how have we converted each of the Python operations into a Zeroknowledge proof operation, stuff like that. Render circuit, if you want to see what the layout is in Halo 2, you can see that. If you see a lot of pink space, let us know, and we'll turn some dials to make the optimization better. Forward lets you run a forward pass, so to know what the quantized model will say your input maps to. So in the example I gave of the scavenger hunt, we use the forward pass to decide whether something's going to work before we actually run the proof. So we know exactly what the model is going to think, what the proof will be able to prove, and then we can decide whether or not to put it in. Jan SRS I talked to. Mock is a function from Halo 2 that lets you, it doesn't construct a proof, but it checks all the equations that describe the proof. Aggregate, again, turns a small proof into into a first layer proof into a second layer proof for EVM verification. Proof, I talked about, this creates the UL or bytecode contracts. This deploys them if you trust the command line with your private key, and you can verify natively, or you can verify the aggregate, or you can verify in the EVM. You can print proof, and you can call for help. I think that's most of what I wanted to talk about. There's some other bells and whistles, like if you get tired of the command line, you can put all those command line flags into a JSON file and pass that whole thing, some other stuff like that. There's benchmarks, and there's examples. So let me leave the last 5 minutes for questions. Thank you.
Thank you so much for the talk. You gave one in DEF CON Bogota, right? Can you hear me now? Can you hear me now? Okay. I was asking if you gave the same talk in DevCon Bogota. Because yeah, okay, perfect. So, okay, no worries. So my question is that the Onyx model supports a bunch of operators, right? Does this repo support all the operators, or? Okay, like what is the percent? 1,500, okay. Uh-huh. Okay, perfect. So can you run the main models with this repo? Like this YOLO model, can you run it? Yeah. Okay. Mhm. I understand. Great, thanks.
Hey, can you change the input parameters between like verifier and generating a proof? So you have these bits and k. So can you change those parameters, or they should be the same throughout the whole?
Maybe the
proof?
same for the prover and the verifier.
Okay,
Yeah.
okay. And for some of the models, k, I think you have to increase the parameters because the proof cannot run or something.
Yeah, you'll have to sometimes. So one way you can think about the situation with zero-knowledge proofs is that there's all these dials, right? Like how many rows there are, how many rotations I use, how many columns I use, and a whole bunch of other things. We're trying to pick some decent defaults and then scale and everything, but you can turn these knobs, and there is some amount of art in terms of like turning these knobs until your proof has the performance characteristics you want. Most of the knobs have positive and negative things. So like I can turn a knob, it makes the prover faster, but it makes the verifier larger. Or it makes the verifier faster, but it makes the proof larger, stuff like that, right? So there's all these trade-offs, and as a field, we don't even understand all these trade-offs. But we're all learning together.
And what's the limit of, say, suppose, number of parameters that should be in the model that your package is capable of
What's the
running?
number of parameters?
Yeah, like how big can the model be?
There's not really a fixed number. It's kind of like how patient you are and how much money you want to spend at Amazon. Yeah.
Thank you.
Last question.
So it's nice to do machine learning on many computers, like a cluster. But it sounds like you can't with this because the AST become circuit is linearized. Is that right?
I'm sorry, can you?
So you wouldn't be able to use Ezekiel with a cluster of computers to do the training or running the model.
Right, so training is a big question, right? So I have two responses to can you do training with this? One is you should think hard about why you want to do training with it, right? Because it better be a good reason because it's going to be very expensive. It's going to take a lot of time and overhead, right? That said, I don't think it's impossible. I think actually that training will start to get easier as proof system innovations kind of hit production. So you can generally avoid it, but what we're proving is an inference pass. It's basically the same cost as a backwards pass. So I don't think it would be too hard to implement that and be able to do training. It's just going to be really slow.
Yeah. Thanks.
Okay. Thank you. And if anyone has interest in building with it or questions,